let's start our first part. So today's topic is equilibrium equations, meaning 2D and 3D. So we'll define support conditions and then unknown reactions for 2D systems and 3D systems as well. And then decide determinacy and stability of a structure and calculate the support reaction of 3D structures by solving equilibrium equations. So the third problem is definitely the most difficult and then comprehensive and topic today. Okay, so let's start with the reaction and motion. So we are not talking about dynamic system, static system, but reactions are related to the motion itself. So what is the bottom line? So reactions developed where the motion is restricted. Okay, so if the body is here and then this body is not moving because of some support, right? And then that support should have some reaction. If this body is moving, then there's no reaction. Okay, it's opposite reaction. So I show you two extreme cases using this cantilever beam. So left side is fixed and the right side is open. Left side, nothing can move or rotate, right? And then right side is open, so it's free to move, right? And then let's think about the reactions. So fixed connection left, there's no motion, therefore all kinds of reactions are developed at this support. So in 2D we have forces in x direction, y direction, and also moment are three reactions for the fixed one. And then the right side is free and all motions, all directions of motions are allowed, right? Translation, right? If there's thermal expansion, right? And then rotations are allowed, so there's no reaction. Okay? So if you remember this, it's you can correlate with these two extreme cases. And there are two in-between cases too, and I show you those options or support conditions with some examples here. So examples in civil structure, fixed connection, this one, it is still beam column joint connection. It is welded here on top of the flange, and then it uses a channel with bolting connection, and then also welding, and they use a stiffener to prevent the motion, right? It's fixed, okay? And then concrete, reinforced concrete structure, also beam column joint, and then there are rebars inside the concrete, right? And then it all casted in on one, right? So it is, this support is also fixed. Okay, so fixed connection has all three reactions developed: Fx, Fy, Fx, Fy, and then moment. Right? Okay, any question so far? Okay, now I talk about the in-between, one of the in-between ones. So the first one is pin. So you see this pin, right? So it is like thumbtack, right? So if you use this plate using thumbtack here, right? And then think about this point, right? And then this point doesn't move because of, right? But it can rotate, right? So that's the pin. And then in a bridge, we can see this, that is a pin, right? And also this is a pin, okay? So let's think about the motion of this pin support. Translation, x direction, y direction, this point, can this point move? Yes or no? No, right? So reactions at x, y will develop. What about rotation? Yeah, rotation is allowed, so there's no moment, right? So there are two reactions developed for the pin. And then the second in-between one is a roller support. So typically we use a circle. You can roll, right? So here's something like this. It's a roller support. And then, let's see, here, do you see this support? So here, this is connection, and then these three rollers are roller support, and it can move x direction. And then we have something like this, rocker. So the bottom side surface is rounded like this, and then beam side is flat surface, so that the beam can slide like through like this, and then shrink, and then expand, something like that. And then this rocker is also considered as equivalent to roller. Okay. Okay. So let's think about the roller's motion. So can this point move x direction like this? Yes. So no reaction in this direction. What about this upward? No, right? So reaction in this direction. And then what about rotation? It's tricky. Yes, it can rotate. No, it cannot rotate. Actually, when you think about this one, it is very little, but it can rotate. The far end of the beam can rotate, like something like this, and then something like this, right? So roller support can rotate, so there's no movement. So for the roller support, we only have reaction in the y direction, typically perpendicular to the support surface. Okay. So we talked about fixed. You have 3 reactions, and the pin 1 to 2 reactions, and the roller just 1. Yeah, and then open, no reactions. Okay. So that's that. And this is the table from the textbook. So you can see this roller support here, 1. And then frictionless pin or hinge or pin, 2. Fixed, embedded, totally embedded, or very strong, no motion, then 1, 2, 3 reactions. This kind of summary of 3 supports. Any questions? Okay. So that's that. And then I have clicker quiz here. So this is a bridge support here, and then this too. How could this support be idealized? So I marked here and then here. And then do you see a little bit of gap here? And there's some bearing or padding between those gaps. Okay. So I activate the quiz. Okay. And then what do you think? Is this support pin, roller, or fixed? So I indicated there are a gap here, and then size of the car is like this, so you can guess the gap, right? It could be a couple of inches, I don't know, and there is a bearing. Okay, are you close after 10 seconds? Okay, let's see the result. Oh, almost tie. Either roller or fixed, not pin. Okay, and so let's think about, start with fixed. So if it is fixed, then it cannot move and it cannot rotate, right? And then there is a gap, right? If there's a gap, then if there's a thermal expansion, then it can a little bit move, right? There's like a 2-inch gap, right? And there is concrete. Then concrete can expand and then shrink under thermal fluctuation, right? And then because of this gap, so can I write here? No? Okay. Because of this gap, this can move in translation x direction, right? And then if this support can move, then what is support condition? Is it fixed? No, fixed support cannot move, right? And if it is moving x direction, then that is a roller, right? Pin support should not move, right? It's pinned and then no moving, but there's a gap here. So in this case, roller is correct. Yep. Okay. And then if we think about this connection, then it is casted as one, right? The column and beam support, right? So for this, we can think of this as a fixed condition. Okay. Okay, now let's move on to the second learning objective. So that is stability and determinacy. So it's kind of difficult word, right? Statically determinate, right? But the definition is simple mathematically. So if we can solve the equation and then find all the reactions, then it's statically determinate. We can determine, right? And then if it is not, then indeterminate, right? So this statically determinate means if number of unknowns are equal to number of equations, because we have 3 equivalent equations. So if we have 3 unknown reactions, then we can solve the equations, right? So then it is easy to solve, solvable with all equivalent equations. So that's determinant. And structurally speaking, statically determinate structure is non-redundant. So that means non-redundant. So one member fails, the entire structure fails. So structural point of view, it is not good. So either biomedical or mechanical, civil structures, we do not pursue statically determinate structure. Indeterminate structure is if we have more unknowns than 3 equivalent equations, and yeah, it's indeterminate. There are more redundancy. So indeed, we pursue this indeterminate structure. So you will, if you are civil or mechanical engineers, then you will finally learn how to analyze indeterminate structure later in the higher level course. But this is static, so we'll start with determinate structures. And then let's see, how can we know? We draw the free body diagram and then count the number of reactions and compare that with 3. So it's more than 3, and you're indeterminate, right? And 3, determinate, right? So that's determinacy. And the second measure is stability. So stability is a measure to see structure, whether structure is properly held or constrained by their support. So stable or not, stable or unstable. Unstable, the structure is moving. Stable, structure is not moving, right? So some mechanical systems are unstable but good. Civil structure should not be unstable, right? Okay. And then some example, a structure will be geometrically unstable, then it will move and collapse if there are fewer reactive forces than equation of equilibrium. That means if we have 2 reactions or 1 reaction, then unstable. We need at least 3 reactions to make the structure stable, okay? So the first one is that mean. And then the line of action of reactive forces are parallel to one another. So even though we have 3 reactions, then if the line of action of those forces are in parallel to each other, then it is unstable. So what does that mean? So let's think about this as a beam. I don't know if you can see from the back. And then these are rollers, right? And then if we have 1 roller and then beam is here, is this stable? It will move or collapse, right? And then what about if we have 2 rollers here? Is this book stable? Somehow if there's no horizontal forces, but we cannot guarantee there's any horizontal forces in the real world, right? There could be wind and there could be thermal expansion, that's a horizontal force as well, right? And then this can move, right? So this is not stable. So these 2 examples are the first one, fewer reactive forces than 3. What about I add 1 more roller here, and then there are 3 rollers, like this. Stable or unstable? Stable, unstable. If there's horizontal force, It is moving, right? If it is moving, then it's unstable, right? So, and what about I add one more roller support and we have 4 roller support like this reaction? It's not the same, so there's a gap, but imaginary roller support here. 4 rollers. Is it stable or unstable? Unstable. So that's the second case. What is the reaction of the roller? Vertical, right? And then if there are 2 rollers like this, 3 rollers, 1, 2, 3. 3 are in parallel to each other, right? And then 1 more parallel to each other, right? So in that case, even though we have 3 reactions, 4 reactions, even 5 reactions, unstable. So that is the second case. And then we don't design that kind of structure. Okay. So this is showing the demo I showed you before. And we cannot guarantee the direction of the force. So it can be random, right? Okay. Any questions? Okay, I think I have some demonstration here, graphical demonstration here. So this is simply supported beam, and then one side is pin, the other side is roller, and then when the pin has how many reactions? 2. Roller, how many reactions? 1, right? So 2 here, and then 1, and then in total we count the number of reactions, 1, 2, 3, right? So it is determinate or indeterminate? Determinate, right? So this is determinate and stable. And then this is 2 roller case. So how many reactions in total? 2, okay. And then it is unstable, right? And then what about this one side pin, the other side fixed? Pin has 2 reactions, and then fixed has 3 reactions in total, 5. And then this is statically indeterminate, right? So indeterminate and it is stable. Okay, so that's the demo. Luckily, we'll use only statically determinate structure in statics. Okay, and now moving on to the third learning objective, so the equilibrium equation. So we talked about how to solve the problem and then find free body diagram and then solve fx and fy equations. So find the resultant. And in x direction and y direction, they are 0, then that's equilibrium, right? And then now we are adding one more equation, that's moment equilibrium equation. So here, that's the first one. And when we solve these 3 equations in 2D, then we can find 3 reactions. So this is the step to solve. And in 3D, we have 6 scalar equations. So 3 directions. Right, so force in x, y, z direction should be 0. And then moment in x, y, z should be 0. So that's the requirement for the equilibrium in 3D. And then these are 2D equilibrium equations. So fx, right, sum of fx, sum of fy, and then moment in 2D, either this direction or this direction, right? Counterclockwise or clockwise. That means this moment or rotation is along the z-axis, x, y, z-axis. So 2D moment equilibrium equation is mz equation. And then for 3D, we need to add fz and then mx and my. What's mx? Mx is along this rotation, so this or this. My is this or this, right? Okay. So that's that. And then these 6 scalar equations can be used as 2 vector form. So sum of all force vector equals 0, and the sum of all the moment vector equals to 0. And then 3D moment R cross F, right? So sum of 3 moments should be 0 too. And we'll practice how to solve these vector forms and scalar forms in the problem solving using the second problem. Any questions? Okay, good. And then now there are so many reactions in 3D because there are so many combinations. But I show you these 3 representative ones to you. So first one is 3D roller. So if this side has only 1 ball, then here force with unknown line of, so this unknown reaction is only vertical reaction, like 2D roller. And then 3D fixed. Fixed is fixed. So all kinds of reactions are developed because there's no motion, right? No motion, all reactions. So in 3D, Fx, Fy, Fz, and Mx, My, and Mz. So 6 reactions are developed here. And then 3D pin, typically ball and socket or rough surface, right? And this point is not moving, but it can rotate in any direction. So there's no moment, but 3 directional reaction forces are developed. Okay. We have 2 problems today. First one is 2D equilibrium equation, and then second one is 3D equilibrium equation, very important. And then I don't have determinacy stability problem because I use only determinate problems for statics. And yep, okay. So problem 4.4, for the beam and loading shown, determine the reaction at A, the tension in cable BC. Okay. So here, there is a beam, right? There's a beam. And then there are 5 forces. Yep. 5 forces, and then we have a pin at A, and then cable at B, and then also pin at C, right? And then should we consider this point C for the free body diagram? No, because it is not part of this beam, right? This beam is connected with this cable. And then as far as we consider the cable tension here, then this beam is taken care of, right? So now let's think about A and B. So A is pin. How many reactions do we have at a pin? 2. So I add AX and AY, and right and upward direction because it's typically positive. Yeah. I don't know the direction. If the result is positive, this direction is correct. If it's negative, we can use the opposite direction. And then B is cable, right? And then what is the direction for the cable tension? Up or down? Downward. Great. Thank you. So you can use B as cable tension or BY because it is vertical. Up to you. Okay, so this is free body diagram, and we don't consider C, so that's very important. And it's 2D equilibrium equation. We have 3 equations, right? So you already know Fx, Fy equations from midterm 1, and then we are adding moment equilibrium equation, okay? And then typically for 2D problem, solve the moment equilibrium equation first, and then solve either force in x direction or force in y direction equation. And you will see why soon. Okay, then as I mentioned before, we will start with moment equilibrium equation. So this is scalar equation, of course, 2D, right? And then we'll count all the moments from the system, and then those moments must be 0. Sum of all the moments should be 0 for equilibrium system, right? System in equilibrium. Okay, then for moment calculation, selecting a reference point is very important because the moment arm is changing based on your reference point, right? Then we can choose any point, but if we choose some point, it's beneficial for us. So between A and B, which one would you choose? Just guess. A. Why? Okay, you already watched the video, okay. Yep, so the rule of thumb is you choose the reference point with the most unknown reactions, right? So A has two reactions. So if we use A as a reference point, and then we can eliminate the moment from AX and AY, and then we can have equation in terms of BY only, then we can find BY, okay? So let's solve MA equation. Next step is defining the positive direction for moment. This is sign convention within this equation, so you can choose either clockwise or counterclockwise. So you have freedom to do that. But I typically choose counterclockwise positive for consistency. And then now calculate all the moments based on A. So A is pivot point, and then calculate moments, so equivalent couple, force couple and the couple, right? So about A, okay? Then what is moment from 15 pound? Force 15 times moment arm, so distance between A to the line of action of 15. So it's 6 plus 8 plus 8, 22, yep, so 22. And the direction. If A is a pivot point like this, right? This is my pen here, right? And then force is this direction. And then this paper is moving this direction, right? And then it's positive or negative? Positive, great. So that's the tip I use. And then next one, 20. So force 20, moment arm between these two A. 8 plus 8, 16. And then same direction, and so positive, right? Okay. This is first time, so I'm taking time, but later I'll speed up. Okay. And then what about moments from 35 pound? 35 times 8, and also plus. Moving on A. What about moments from 20? 0, 20 times 0, right? AX times 0, and then AY times 0, good. And then next, 15, moment by 15. 15 times 6, plus or minus? Minus, great. And then the last one here, BY. BY times 6, and same direction, so minus. Okay, then if you have calculator, use calculator, and then to find what BY is. Yep. So this is what I have, 840, and then divide by 6, so it's 140. Right? Okay. So any question about the moment equilibrium equation? Okay, so I strongly recommend to write down moment equation, moment MA equation on your own after this lecture to strengthen your skill. Okay, so here we found the cable tension here. So there's 140 pounds, good, positive. So it's cable tension, not cable compression, cable tension, right? And then now we move on to Fx and Fy equation. So Fx equation, so that's what we already did. So if I may assume right side positive, then what do we have as horizontal force only AX, right? So AX must be 0. And then Fy equation, if I may assume upward positive, then we have minus 15, minus 20, minus 35, minus 20, minus 15, minus By, plus Ay, right? So I write that down. By is 140, right? And then everything is negative, so Ay should be sum of all these numbers. Yep, 245. Thank you. So at A, this is spin. There are two reactions, but AX is 0, AY is 245 pounds, and the BY cable tension is 140. So that's 3 unknown reactions for this system. And then one thing to remember is if there's a beam and then there's no horizontal force, right? Then your horizontal reaction here, AX, is always 0 because there's only one term, AX, and then AX must be 0. Okay, any questions? Okay, then move on to the 3D problem. Very important problem, okay? So a 10-feet boom is acted upon by the 840-pound force shown. Determine the tension in each cable and the reaction at the ball and socket joint at A. Okay. Too difficult? Okay. So there is a beam or rod, something like that, where it says beam, right? And then one side is free. The other side is ball and socket joint, and then that is 3D pin. Okay, 3D pin has no moment but 3 force reactions, right? So that's what we can remember, right? So this is a pin, and then this is 3D pin, so there are 3 forces to include in the free body diagram. So that's what we need to think about. And then there are 2 cables connected here, BD and then BE, right? And then, yeah, for convenience, yeah, I already calculated this one directional vector, but we don't know the magnitude for both cable tension. So what we need to find out is 2 cable tension here, magnitude, and then reaction at A. So that's the difference. So in the force equilibrium before, we thought about one point, right? One point, and then if there are some forces, multiple direction, then we just sum all the force vectors together and then make it 0, right? And then this one is considering entire system and thinking about the reactions and other cable tensions at B and then forces at C. So we think about all system. So for the system, we have 6 scalar equilibrium equations. So meaning 3 force equilibrium equations and 3 moment equilibrium equations, or 2 vector equilibrium equations. Sum of all the forces, 0, so that's what we already know. And then sum of all the moment equals to 0, so that's what we will solve today, right now. Okay? So this is 3D equilibrium equation, so I'll add these 2 vector equation. Sum of, so sigma moment vector in the system, and then sum of all the force should be 0, right? So these 2 equations are what we'll solve today here. And then like 2D, always start with moment equilibrium equations first. Then we will solve some unknown reactions, and then move on to fourth equivalent equation to find the remainder of unknowns. Okay. Okay, are you ready? Okay. Then, now start with moment equivalent equation, 3D. So we cannot assume any positive directions, 3D, any directions possible, right? And then for moment equivalent equation, we need to find or use the reference point, right? And then before that, let's plot the free body diagram. So C, we have force here, and then two cables, cable tension. So I use this direction, cable tension away from point B. So I use TBE here. So B to E. And then this one, TBD. I'll add the force here again. And then at A is 3D pin, so I use 3 forces, AX, AY, and AZ. So I use broken lines to indicate the reactions. So this is the free body diagram for this problem. And then now moment equivalent equation here. And we need to choose the reference point. And we have 3 options, A, B, C. Which one would you use? A, B, C, A? Either A, B are good option. Because if you choose A, you can find TB and TBD. If you choose B, then you can find AX, AY, AZ, and then cable tension later. So A, B, either are fine. But let's use A, because A has 3. So let me use red pen to indicate the reference point. Okay, and then now we need to count all the moment, all the 3D moment from the system. Okay, so 3D moment, R cross F. And then we have how many forces? 1, 2, 3, 4. Let's use reaction at A as RA. And as a 1 force vector, and then this one as 1 force vector P. Okay. Then there are 4 forces, 1, 2, 3, 4. And then 4 moments, right, terms. So let me see. Let me write down like this. R cross F. So first one, let's use TBD. And second one, R cross TBE. Second force. This one. And then we'll figure out what position vectors are later together. And then third one, R cross P. And the last one, R cross RA. So I think I wrote down all the moments from all 4 forces in this equation. Okay, any questions so far? Okay, then now position vector. So position vector is a vector connecting the reference point to the point of action of that force, right? And then what is the reference point? A. Yeah, reference points, same for all with everything, right? So reference point is A, and then point of action for TBD is B, right? So I use B. Okay, so first position vectors covered. Next one. What's position vector? A, B, right? Reference A, point of action B. And then the third one, AC, reference A, point of action C. And the last one, reference point A, point of action A. What's AA vector? 0, right? So this is 0 vector. So 0 cross something, 0. So we don't have to consider that. So it's consistent with 2D, right? If there are forces at one point or reference point, there's no moment effect because moment arm is 0. And then here position vector 0. Okay. And then also some other tip. So if once you choose the reference point, in this case A, then you can use the first subscript as A. So A, mechanical A, and then find out the point of action based on this force. So it's B, so write down B here, and then P, look at this, and then C here. So RB, AB, and then AC. Okay. Yes?
What is vector RA stand for again?
Vector RA here is reaction at A. Yep. Okay, good. Any questions so far? Okay, and then having this equation is the most important thing in solving this problem. Okay, other than finding 3D component and then conducting cross product, and then you will get minor deductions from exam. But if you messed up with these indices, then yeah, it's wrong, right? So, okay, then now let's try to solve it. So here, 3D force vector for 2 cables are given. And then what about the force, so external force here, 840. What is magnitude is 840 pounds. And what is the direction vector for this? Downward. Negative J. Right? And then RA is reaction, indicating reaction at A. And we have 3 components, AX, AY, and then AZ. So R at A, X magnitude, I direction, AY magnitude, unknown, and J direction, and then AZ, K direction. So finally, I answered your question. So RA is AXI, AYJ, and then AZK. Okay. Any questions? Okay, then now it's calculation time. So RAB, what is our RAB? RAB is this vector, and then magnitude is 6 feet, and then direction of RAB is along the x-axis, positive x-axis, so 6i. And then RAC, A to C, 10I. Great. So now with this, let's solve this equation. You don't have to use calculator, okay? Just follow me. Here. First one, 6i cross TBD here. So TBD, and then I use minus 6 over 11i, 7 over 11j, 6 over 11k. Okay, and then the next term here, RAB cross TBE. So it's the same. So 6i cross TBE, unknown K potential, and then minus 6 over 11i, 7 over 11j, minus 6 over 11k. Okay. And then the third term, RAC, 10i cross P minus 840j equals to 0. Right. And is there any x component? No, none. And then y component in front of j, right? So minus 36 over 11 TBD, and then plus 36 over 11 TBE, Okay, so it's 0. And then the coefficients are the same, right? So from here, we can see these two cable tensions are the same. Right? And also from the figure, it's 6 feet, 6 feet, and 7 symmetric, right? So it should be the same physically, right? And then Z component in front of K, right? So 42 over 11 TBD. And then 42 over 11 TBE. And then minus 8,400 equals to 0. Right? And from the Y equation, we found these two cable tensions are the same. So let's use this one as TBD. Right? And what happens? So because these two are the same, then we can sum these two up, right? 42 over 11 plus 42 11. So 84 over 11 TBD equals 8,400, right? Then 84, and then TBD should be 1,100, right? And then because these two are the same, TBE is also 1,100 pounds. Right? Okay, so now I'll show you something like this. Right? Okay, any question about this? Okay, so first part, we solved moment equivalent equation and then found two cable tension. Is that all? We need to find the reaction at the joint A. And to do that, we need to solve the remainder of equivalent equation. That's force equivalent equation. So that's what you are good at, okay? So I use the second page, and then use force equivalent equation. Okay. Okay, so there are four forces, right? So I write TBD and then TBE and P and reaction at A equals to 0. So the new thing in the force equivalent equation is adding the reactions. If you don't add the reaction, you cannot solve this problem, okay? Add the reaction. And now we found this magnitude is 11,000, right? So if this is 1,100, right? Then what is TBD? So 11 canceled and 100. So first one is minus 600J plus 700J plus 600K. So that is TBD. Okay, I repeat. So here, magnitude, if magnitude is 1100, then this 11 is canceled and we have 100. And then multiply 100 times minus 6, 100 times plus 6, 7, 100 times 6 here. Okay, and then the second factor, this one, this is also 1100, right? So we are multiplying 100, so minus 600I plus 700J minus 600K. And then the force is already given, minus 840J, and adding important RA. So that's AXI, AYJ, AZK. So now we all finished midterm 1. So if you see this one, you can easily find AX, AY, AZ, right? So X, Y, Z component, or you can look at I components, minus 600, minus 600 at AX. So it should be 1200, something like that. So I write it here. So X component, minus 600, minus 600, plus AX. So AX is 1200. And then Y component, so I'm going to go through fast because it's already, you already know. So 700, and then 700, and minus 840 plus AY. Right, so then AY in my note is minus 560 pound. And then Z in front of K, so 600 minus 600 plus AZ. So AZ is 0. And the final answer, reaction at A, use these two components and the directional vector. So 1200 I minus 560 J, the unit is pound.